Hello and good afternoon, everyone, and welcome to our special webinar this afternoon entitled Effective Casting Simulation. Thank you for joining us. My name is Jared Weaver, Executive Director of the Non-Ferrous Founder Society, and I'll be the moderator for this afternoon's session. Our presenter is Dave Schmidt of Finite Solutions, Inc. Dave will provide us with an overview of how casting simulation software can be used in the Foundry to tremendous success. Be advised that we are recording this webinar and a copy will be made available on the NFFS website within 48 hours of conclusion of this session. If you have any questions, please enter your questions directly into the chat window and we will address them as they are presented. Copies of the webinar slides will be made available to our webinar attendees upon conclusion of the session via email. Please look for an email from the Society later this afternoon. And with that, we're ready to begin. Dave, if you would, please.
Thanks, Jared. Hello, everybody. I'm Dave Schmidt of Finite Solutions, and as Jared mentioned, we're going to be talking about casting simulation. Brief agenda here. Going to give you a very quick introduction to the concept of simulation and a little bit of information about who Finite Solutions is. Talk a bit about simulation benefits. Give two very brief case studies showing how the software can be used, and then summarize with benefits to the members of the non-ferrous founders. Finite Solutions has been around for quite a while. Actually, we were the first company to commercially provide PC-based simulation tools. This slide shows a few of our company milestones. We started simulation in 1985. That was in the days of the MS-DOS operating system. At that time, I was employed by the American Foundryman Society, and Larry Smiley, who is the president of Finite Solutions, worked in the foundry industry at Reliable Castings, where he developed the world's first simulation tool. It started as a 2D program and was expanded to 3 dimensions in 1992. And as you can see, the various dates, things moved forward. We started in 2D, moved to 3D, went from DOS to Windows, and added more and more features and capabilities, starting with solidification, adding fluid flow analysis, and then also process optimization. We continue to not only develop, but expand the use of the software. So there's many, many more features now than there were originally. And of course, with computers getting more and more powerful, the capabilities, the things that we can do with simulation, really we didn't even dream of being able to do back in 1985. There's actually 3 pieces to the software that we'll be discussing. SOLIDcast is the main module or the main system that includes model building, the databases of materials, both casting alloys and mold materials, the filling process, solidification simulation, and predictions of porosity. FLOWcast adds true flow modeling, which is based on a tool called CFD, or computational fluid dynamics. This allows us to simulate in great detail the mold filling process and the prediction of defects related to that filling process. It also provides the most realistic and accurate temperature distribution due to filling, which in turn improves the solidification analysis. And finally, optimization is a tool that can be used to fine-tune your rigging design. Normally, this is done to obtain the maximum process yield while still guaranteeing casting quality. When we talk about casting process design, we need to look at what the goals are. In other words, what do we want to do when we're working with process design as done by simulation? And of course, the first answer, the most obvious answer, is to make good casting. We would like to do that as efficiently as possible and as quickly as possible. Simulation is just estimating or predicting what's going to happen on the shop floor. By doing it on the computer, we are hopefully saving time, money, and doing things more reproducibly from one casting to another. When we look at process design, we can break it into 4 pieces. We can start out with the customer specifications and data. That would be things like a blueprint or a CAD model, as well as process details. We then come up with the initial design concepts. How are we going to rig this part? How are we going to gate it and riser it? The third step is verification through simulation or through shop floor trials that show that the rigging design we've come up with will work acceptably. And then finally, design optimization, where we can take that rigging system, fine tune it so that we can get the highest process yields while still guaranteeing our level of casting quality. Let's take a look at these pieces and see how they fit in with the software. For customer specs and data, we work with the SOLIDcast system, and this is done through a CAD import. SOLIDcast uses STL or stereolithography files, which are a very common file format that virtually any 3D CAD system today can provide directly. The design concepts are created through the riser design wizard and the gating design wizard, which are electronic worksheets within SOLIDcast that allow us to use simulation to help us design the rigging system. That is, we run a simulation of the part without rigging, and these wizards help us to determine a good gating and risering design. Verification of that design is then done using SOLIDcast and FLOWcast so that we can do a fluid flow analysis to check the filling situation, and then SOLIDcast to do a solidification simulation to verify that we're going to make a sound casting. And then finally, optimization can be done using the OPTIcast tool. Let's look at these in a little bit more detail now. Mentioned SOLIDcast, the idea is that we have design tools up front so that simulation actually helps us to design a good rigging system, not simply test an existing design. And this is done, first of all, through the use of the riser design wizard, which helps us to find the appropriate location for risers, the appropriate size for the riser, and allows us to test and verify the use of these tools. For example, we could work with a sand riser, we could work with a sleeved riser. There's a lot of different options there, and the riser design wizard takes us through that process. The traditional approach to riser design is commonly called the modulus approach or the modulus method. The modulus is simply the volume of the casting divided by the surface area. Now, that could be of the full casting, or it could be for different parts of the casting. And this was really a concept that was developed almost 100 years ago. And the idea behind it was that the volume represents the heat or the energy that needs to be removed in order to get solidification to occur. And the surface area is where that heat goes. So if you have a given size casting, you have a given amount of volume. If you have more surface for that heat to flow out, then that heat is going to be removed more rapidly and will have a quicker solidification time. So the modulus becomes a rough equivalent of solidification time. However, in the computer age, we can do a lot better than that. We can calculate what we call a thermal modulus or an effective modulus, which is based on an actual solidification analysis based on the actual properties of the casting alloy and the mold materials in question. This gives us a more accurate analysis and thereby allows us to go back and do a more accurate riser design. In the same way, we have a gating design wizard, which allows us to calculate all the pieces needed for a gating system: sprue size, runner size, gate size, and these are calculated in order to achieve what we call an optimum filling time. Again, that is calculated by the system, and we can make choices, and the system will go through and calculate appropriate sizes of all the components of the gating system. We can work with either horizontally parted molds, and this is a schematic taken from the AFS book, Principles of Gating Design. And we can also work with vertically parted molds, such as you'd have on a D-Zematic molding machine. Incidentally, a lot of the principles for gating and riser design can be applied to the investment casting process and the permanent mold process as well. So once we've designed our system using the wizards, we can then use SOLIDcast and FLOWcast to verify or to test that design. And then finally, if we wish, we can optimize that design, fine-tuning it to get the highest yield possible. Let's now look at the actual steps in simulation. We start off with materials. What's our casting alloy? What's our mold material? What is our molding methodology? That is, are we doing sand casting? Are we doing investment casting or permanent mold casting? In each of these situations, we have different ways to set up a simulation to accurately model the system. The second step is to create a three-dimensional model. Generally, the simplest way to do this is to get a CAD file from your customer. Again, our initial simulation will be without rigging, so model building normally only takes a few seconds. That is, import an STL file, tell the system what the alloy is and what the mold material is, and go on to do the simulation. Of course, when we add things to that model, the rigging, the risering, the gating, perhaps the use of chills or other materials, those can be created either in CAD or in many cases can be done within SOLIDcast as well. The simulation itself is not actually run on a CAD model. It's run on what we call a mesh. In SOLIDcast, we break the model down into a series of cubes, which we call nodes. And this may be a few 100,000 cubes to many millions of nodes, depending on the size of the model and the complexity of the shapes. The meshing process is done in an automatic fashion. We set a few parameters and the meshing takes place automatically. Running the simulation can be very straightforward. The initial simulation without rigging is typically done without a filling analysis being done. We assume that the mold is full instantaneously. We can also use simplified filling contained in SOLIDcast or more complex filling using FLOWcast. When the simulation is done, we plot the simulation results in various ways, and there's various pieces of data we can look at to determine have we done a good job or not. It's then by analyzing those plots, we can decide whether we need to make adjustments to our process or not. The current way we do this, or the manual way we work at this process, is shown in this schematic. We start with the foundry engineer who looks at drawings or CAD files, comes up with an initial design, and then we run that through simulation to see did we make a good casting or not. If we look down at the bottom of the screen, then we can see that once again, the foundry engineer is involved deciding whether things are good or bad. If things are not acceptable, decisions are made on what to change, adjust or revise the design, and then resubmit that to process simulation. Now, this loop may be gone through several times before we get what we would call an acceptable result. However, we are trying to develop a new paradigm where we can do a lot more in a lot less time. And that is by using the system to help us with the decision-making process. We start with the foundry engineer once again, but in this case, the initial design is run automatically by the system, and then gating and riser design wizards are used to help us with that initial design of the rigging system. That is then submitted to simulation, and now we can either use the foundry engineer to determine whether things are good or not, or we can insert optimization into the process, where the system can automatically determine, was the result of that simulation acceptable, and also to determine what should be changed. And essentially, it automates this bottom process. So there may be many simulations done, but an operator is not involved once the optimization is begun. And we'll see in a minute how that is done. That allows us to improve our results. Typically, we can get yield improvements in the order of anywhere from, say, 5 to 15%, and yet have less time involved with the simulation process itself. So let's take a look at a couple of examples of how we would do this. We don't have time today to cover all the processes, but we're going to be doing a brief case study of an aluminum casting made in a sand mold, and then also an investment casting. This is a capstan casting, weighs, well, I've got it in kilograms here, 61 kilos, so about 125 pounds. So it's a rather large aluminum casting. When we run a simulation, we tell the software, what is our casting alloy? That is simply selecting the material out of a database. And what is our mold material? Again, typically we're just selecting the material out of the database. In the case of sand castings, we can have various binder processes. So we could have, say, a green sand mold, we could have a phenolic urethane binder, any number of things there. And we pull that data just by checking an entry on a box in the database. In the case of the casting material, we're normally adjusting the pouring temperature for the particular process we're working with as well. Setting up and running this initial simulation normally only takes a minute or two, and running of the simulation itself, depending on what PC you have and the complexity of the model, typically only takes from say 2 or 3 minutes to approximately an hour for a very complex model. This shows a plot of the solidification time, where basically we're looking at the darker colors representing the faster solidification times and the brighter colors, the longer times. Once we're done with the initial simulation, we go into the riser design function, and we have a little worksheet like this. If we take a look at the casting over here on the right, we can see the area where the last point to solidify is basically in the center of the casting. And the simulation has, or excuse me, the riser design wizard has all the data from the simulation so that we can go through riser size calculations. We can see here we have the choice of using no sleeve, in other words, a sand riser, or using an insulating or exothermic riser sleeve. And we have a number of options. The system goes through and it verifies 2 things when it's doing a riser size calculation. Number 1, it's doing a thermal calculation, making sure that the riser freezes after the section of the casting that we're trying to feed. It does this by ensuring that the thermal modulus of the riser is greater than that of the casting. Normally, we assume 20% greater modulus for the riser. It also needs to check to make sure that there's enough volume in the riser in order to provide enough feed metal to feed the shrinkage that would occur otherwise in the riser. And this just shows a summary of results here, and it tells us here that the riser volume is okay. So we can calculate the diameter of the riser, the height of the riser, and make sure that the modulus information is greater than the casting modulus, and then our volume information is adequate as well. If any one of these pieces is not satisfied, it will be flagged in the screen, and then you can very quickly go back and make adjustments to see what changes need to be made in order to get an appropriate size riser. In the same way, we can use the gating design wizard, essentially an electronic worksheet where we go through, the system will pull the weight information out of the model. We select the type of alloy we're working with, and we enter what's called the critical section thickness. In other words, the thinnest section that we would need to fill during the filling process, and that would be down on this lower lip here. When we enter that data, the system will calculate an appropriate filling time for us based on the overall weight poured and that critical section thickness. We can make adjustments to that filling time if we wish, but once we enter a filling time here, the rest of the gating system will be calculated in order to meet that filling time. So the sprue, the runner, and the gates are all sized so that we can meet that filling time. Going further into the gating design wizard, we can make choices of, do we want to have top gating, bottom gating, or parting line gating? And when we make changes to that by clicking on these buttons, the schematic will change, and then we can enter pattern dimension information. We can have a choice of a round or a straight, or excuse me, a round or a square sprue, and either straight or tapered. And the system will calculate what's known as the effective sprue height. This refers to the height of the metal that's falling, and that's what provides the metal velocity within the gating system. We can enter a gating ratio, which is the area of the cross-sectional area, or excuse me, the ratio of the cross-sectional area of the sprue to the runner to the gates. So in this case, we have a 1:6:6 ratio, the sprue being the smallest number. This is what we call an expanding or a non-pressurized system. And then we can set the number of runners and the total number of gates. The system then goes through and calculates all the appropriate dimensions for the sprue, for the runner, and the gates. This shows what the gating and risering system looks like based on those calculations. We can see that we have top risers here with insulating sleeves. We can see that we have a round tapered sprue. We have a double runner. Incidentally, when we look at the runner, we can see that this is what's known as a step-down runner, which allows equal flow through each gate. You can see after the first gate, the thickness of the runner is reduced. That's so that we maintain a constant cross-sectional area and a constant flow rate through each individual piece of the gating system. Also notice that we have a green disc on the top of the sprue. That's called fill material. That allows us to run a filling simulation that essentially becomes the source of hot metal into the system. And also, we have a filter down here. SOLIDcast has a utility that will allow you to create ceramic filters. And we actually modeled the flow through down the sprue, through the filter, and through the gating system. This just shows another angled view. And this also shows that we'll be using a chill on the base in the center of the casting. The reason for this is with our initial simulation, we found that we could not get good feeding continuously through from the top riser down into the bottom part of the casting. So we used a chill to freeze off that area quickly and promote directional solidification. Just another view. And here we're going to see a couple of screenshots showing the filling process. This shows a 20% increment. We're looking at the temperatures that are changing during the filling process. And if we broke it down and created a movie, we would be able to see the entire filling process in a smooth, in a real-time sort of fashion, so that we could see if there's any splashing or formation of areas where gas would be trapped, things like that. Incidentally, when a filling simulation is being done, we can look at the temperatures, we can look at metal velocity, we can also look at pressures. And so this just shows steps through the filling process. This shows metal velocity. We're looking at getting flow of metal in as calmly as possible, especially in the non-ferrous alloys, because they tend to be prone to dross formation and getting oxide mixed up. So we're looking here, we're getting nice, slow metal velocities. So our lower values, the dark and medium blues. And in this case, we were doing a plot of anywhere where the metal was going faster than 0.5 meters per second. And this is sort of a typical cutoff value. We would like to keep the metal velocities below that, and we can see that we're doing that quite well here. The only area where it's going faster than that is the initial metal down into the sprue. If we look at solidification, this is a plot of the temperature distribution at the end of solidification. And this is a plot of solidification time. Generally speaking, we're looking for directional solidification, where we want to see different parts of the casting solidifying in a progression of darker to brighter. And we want to go out so that the last point to solidify is in the riser. That appears to be the case here. We can slice things through the middle and see, again, we're getting a good progression color change through here from the dark blue through the purples up in the reds. And our last point to solidify is in the riser. This is an X-ray plot, or what we call an isosurface plot. We're plotting material density, which is our predictor of macro porosity or shrinkage. We can see the piping in the risers and the fact using the sleeve that, excuse me, by using the sleeves that slows down solidification, and we can see the piping. We can also see some shrinkage in the sprue and at the base of the sprue. This is at a value of 0.9. In other words, nothing is shown unless that area has lost 10% of its nominal density. Here we're plotting at 0.95, so it's a higher sensitivity. Anything is shown that has lost more than 5% of its nominal density. 0.99, this is 1%. We can see we're getting a little indication here at the gate connections. And then finally, at a value of 1, this is our highest level of sensitivity. In other words, any degree or any loss of metal density will be indicated in the plot. So we can see that we have more indications in the sprue. We can see better the piping of the risers, but we can also see that the casting is completely clean. And in fact, if we go from a side view here and rotate the casting so that the sprue and the gating are out of the way, we can see that we have a perfectly sound casting. So by doing an initial simulation with SOLIDcast, we were able to determine the basic solidification behavior of the part. We were able to calculate appropriate size risering, appropriate size gating, and then by adding those to the model and running a verification simulation, we can see that we're getting a perfectly sound casting first time through, which of course is what we're hoping for. This is just another view from the top. Just a couple of things showing here. I mentioned after running a first simulation, we weren't getting good feeding all the way through. In other words, the feeding zone was separating out. This shows an example of what I would call an intermediate model. That is, we're not showing an entire gating system, but what we're doing is we're adding the in-gate locations and making them out of fill material. By doing this, we can put hot metal in here without doing a rigorous filling simulation. That saves us time, but it also gives us a good idea of what's happening with the filling process or the effects of the filling process. After putting in that chill, we still weren't getting complete progression of solidification through. So we actually made an adjustment to the casting geometry by adding a circular pad on the inside, again, doing simplified filling. And we were able to then verify that the risers could then feed through and completely feed the casting. And then finally, our final simulation, or simulation number 5, that was done with the entire gating system and also done using what's known as a plane of symmetry. You can see here that the casting itself is radially symmetric, but when we add risering and gating, we have a plane of symmetry or a mirror image right down the middle. The reason we do that in simulation is that allows us to run a simulation twice as fast, yet give us results that are exact. There's no loss of accuracy from this at all. And so if we're lucky enough to have a part where we have symmetry involved, that will allow us to run our simulation that much quicker. Let's take another example, very quick look at adding the idea of optimization to the process. This will be done for an investment casting. This shows the wax pattern, and you can see initially that one of the problems that they were having at the foundry was that they were getting internal shrinkage in the casting below the in-gate. So they were actually gouging out so that you can see the shrink area below the in-gates here. Initial simulation was done to make adjustments trying to move that shrinkage out into the gating system. And that was actually done by putting a little wedge underneath the gate to open up the area through there. So this became our starting point, and then added the current gating system into the model so that we can do an optimization. And we can see a couple of things here. We have the casting geometry, the gating system in blue, and fill material at the top in the green. So we're doing a filling simulation with this as well. When we're putting together an optimization, we need to tell the system what things will vary, what things will change. That is, what features of the gating system. In this case, we have a horizontal feeder bar that will vary. We have a pouring cup, and we have the in gates. Now, with each variable, we have some adjustments we can make. We can say, how much bigger, how much smaller can it get? Are there things that are not allowed to change? For example, here, we don't want the gate height to change because that would pull the casting away from the rest of the gating system. So we're fixing that height. We also have what's known as a pinpoint location. That is, where in space is this variable going to be fixed? We're going to link the left gate to the right gate. Once we have told the system what variables we have, we need to tell it what constraints we have. In other words, how does the system determine good from bad? Well, in this case, we want the casting to be shrinkage free. So we say we want a minimum material density of 1. 1 is a perfectly sound or no loss of density whatsoever. As you can see, we can have a number of constraints depending on what we're looking for in a particular model. The most common thing, however, would be a shrink-free casting, which would be a material density of 1. And finally, we need an objective. That is, what are we trying to do through this optimization? Most frequently, that will be maximize the yield. In other words, get the smallest pouring weight that will give us a sound casting. Once we've set that up, the system runs on its own. And in this particular example, it actually ran 50 simulations. So originally when this happened, that was an overnight run. This was an example we did a number of years ago. With today's computer, you could probably do those same 50 simulations in a couple of hours. This shows the summary. The initial situation, we had a process yield of about 38%. The final yield was 53%. So we had approximately a 15% improvement in yield. This shows a chart of how the soundness varied. That is the shrink factor through those. Our final value comes out with a value of 0.9998, which actually is not our value of 1. But when we're doing optimization, we can allow what I call wiggle room. It's called a percentage of a constraint violation. We allowed it to vary up to 0.05%, and that would still be acceptable, and we're well within that range. This shows how the feeder bar changed in size. It was originally at a value of 1. It dropped down to 82% of its original size. And for the feeder bar, the height dropped to 83%, so about the same each way. The pouring cup, the size of that dropped down to about 42% of its original size, so that decreased quite a bit. And the gate actually got a little bit bigger, and that was in order to promote directional solidification. Let's look at a comparison. These are slices through the two models showing the solidification pattern. This shows the initial area where we were getting shrinkage or a hot spot inside the casting. This shows the change where that was pulled up out of the casting and out into the feeding system. Here's our shrinkage predictions. Originally, we had shrinkage in the casting. And finally, there's no shrinkage in the casting, and our yield is 15% greater at the same time. So we've been able to get a great improvement while improving casting quality at the same time. This shows what the rigging systems would look like. And the result with that 15% improvement eliminated shrinkage from the casting, and with the production quantities that saved the foundry about $17,000 a year in this part alone. So those are two examples of how this system can be used, one for sand casting, one for investment casting and adding an optimization. The permanent mold process is a bit more complicated, but we have many tools that allow you to set that up and run permanent mold simulations. We don't have time in this short webinar to be able to go over that, but if there's anyone who is interested in seeing a case study or two of the permanent mold process, you can just let me know and I'll be happy to send a similar sort of thing to what we see here on that you can look at your leisure. So one of the questions is, what would be the member benefits are using simulation? Of course, anybody can benefit from that, whether they're a member of the Non-Ferrous Founders Society or not. But the question is, what benefit could you get directly by working with simulation as an NFFS member? Well, money savings is the basic thing. Essentially, what we would do is we would treat you as a group. There are foundries out there that are members of groups, and we do provide multiple discounts to those companies if they group together. But essentially, we would treat every Non-Ferrous Founders Society member the same and give a discount of 25% on the software. The software is sold by the site so that you can run more than one instance of the package at a given foundry. So if you had 5 computers, you could actually be running 5 sets of the software. There's no additional cost for that, but this would be a total savings of 25% to the foundry. The second area is that Finite Solutions will be providing focused training groups. And what I mean by that is we typically run shorter seminars of training for specific processes, for sand casting, for investment casting, for permanent mold casting. For the non-ferrous founders groups, we would do that, and we would further tailor that to the alloys and the materials you're working with. Typically, what we can do is we can start off with one of your parts and then use that as a case study for the training process. So not only do you get to see how the software works, but you get to see it work in a specific part from your foundry. The third area that we can provide benefit is on our annual support update contract. That's included with the software for the first year at no additional charge, but there is a fee for that on a yearly basis. We would provide a 10% annual savings on that as long as you remain an NFFS member. So that would be a continuing savings on a yearly basis. Wow. So that is a very brief overview of simulation, what it can do, and how we can help NFFS members. If there are any questions people have right now, I'd be happy to answer them. Jared?
Yeah, Dave, thank you. That was a great presentation. I think it's a great review of the fundamental capabilities that simulation modeling can provide to our Foundry members. I do have just a couple of questions for you. Obviously, this is some software that we would like to deploy into individual foundries. Mm-hmm. for the foundries that may not want to purchase a full-blown program or are able to staff such a program, do you offer any kind of assistance for one-off type projects?
Yes, we do. We offer contract simulations all the time. I mean, there's several of those being done. What we can do for a foundry, if you're a member, we would provide the same sort of discounts off our contract consulting rates. We always quote on specific jobs. We don't have, like a per hour thing or something like that. What people would normally do is they would send us a CAD file or a drawing. And depending on what they specifically wanted done, whether it was a new rigging design or whether they're trying to solve an existing problem, we would quote the foundry for that specific work. And then we would, as I said, we would provide the member discount on that if people chose not to do that. That's also very common for people that are interested in simulation, but if they don't have any experience so far, just to see what simulation can do and sort of prove things on their jobs, even though they may eventually want to get involved with the software at the foundry.
Great, that's very helpful, Dave. The other question, I actually have two more questions queued up here. One is the resulting output of the simulation process results in a 3D model of both the casting and the gating design. Is that output suitable for use in perhaps a printed sand mold or creating some kind of short run tooling?
Sure, the answer to that is yes and no. The reason I say that is that we do not work specifically with one CAD system. That is, the software is not tied to, say, SolidWorks or AutoCAD or whatever system. That being said, most people will be doing their design work within CAD. SOLIDcast does have a model builder, but it certainly does not have the level of sophistication or complexity that the common 3D CAD systems have. So in that sort of scenario, most people will be doing their design work within CAD. They'll then export as an STL file or a series of STL files into SOLIDcast for simulation. So the same model that would be used for simulation can also be used for other outside processes. So as long as the modeling work is being done from the CAD system, then they should be able to do that sort of thing very directly.
Great. And Dave, I have one final question for you. This was actually submitted by a user via email before the session actually started, but they wanted to know if Finite Solutions has any plans or ability to incorporate and model a Campbell gating design for aluminum alloys, and specifically the impact of bifilms. Is that something that your system can handle now? And if not, is it something you plan to adopt at some point in the future?
I've talked with John Campbell at various times. I will confess that I didn't read his book because I got out of school a long time before he got started. However, I will say generically, we can simulate anything that you can create a model for. So I know that one of our users, University of Wisconsin-Platteville, Kyle Metzloff there, has done a lot of work with things that Campbell has done. We have not made any special adaptation, but if I could get details on what they truly mean by a Campbell system, we would certainly look at it. And if we can't do things directly, we could let them know what we would need to do in order to be able to look at that. Generally speaking, we're pretty responsive to that. One of the advantages of being a small company is that when you talk to Larry, you're talking to the main technical developer directly. And also, when we're working with fluid flow, we have another gentleman who is a real expert in that. And the advantage is you talk with them directly. And so we can make adjustments and changes. And in many cases, get those out into software that can be distributed literally in a week or two.
Great, Dave. I take it to mean if the Foundry can model the gating system, you can run the simulation on that model.
Yeah.
Great.
But if you want a specific example of something, all we need is a description of what that is, and we can work through it very quickly.
Great. Dave, I have no other questions from the audience or previously submitted. So with that, I would like to thank you for your presentation. I think that was very helpful. And we'll be sure to share this with the rest of our membership. Thank you for your time and contribution. On behalf of Dave Schmidt, this is Jared Weaver with the Non-Ferrous Founders Society. Thank you for joining our session. Have a very safe and productive afternoon.